Okay, we're starting to move into types of electricity. This is electrostatics. This is going to be in two parts. This is part one of the notes. Electrostatics involve electric charges, the forces between them, and their behavior in materials. Electrostatics, or electricity at rest, involves electric charges, the forces between them, and their behavior in materials. An understanding of electricity requires a step-by-step approach, or one concept is building the block for the next. The fundamental rule at the base of all electrical phenomena is that the charges repel and opposite charges attract. So if two positive charges, they will repel each other. Two negative charges will repel each other, but a positive and negative charge will attract to each other. Consider a force acting on you that is a billions upon billions times stronger than gravity. Suppose that in addition to this enormous force, there is a repelling force, also billions upon billions times stronger than gravity. The two forces acting on you would balance each other out and have no noticeable effect at all. A pair of such forces acts on you at all time. These are the electrical forces. The enormous attractive and repulsion electrical forces between the charges in Earth and the charges in your body balance out, leaving the relatively weaker force of gravity, which only attracts. So gravitational forces we've talked about before. Gravity only attracts, but electrical forces and stuff like that only, well, not only, they repel and attract, depending on the charge. With the atom, the electrical forces arise from particles in atoms. The protons in the nucleus attract the electrons and hold them in orbit. Electrons are attracted to protons, but electrons repel the other electrons. The fundamental electrical property to which the mutual attractions or repulsions between electrons or protons is attributed is called charge. By convention, electrons are negatively charged and protons are positively charged. Neutrons have no charge and are neither attracted or repelled by charged particles. The helium nucleus is composed of two protons and two neutrons. The positively charged protons attract the two negatively charged electrons. Here are some important facts about atoms. Every atom has a positively charged nucleus, surrounded by negatively charged electrons. All electrons are identical. The nucleus is composed of protons and neutrons. All protons are identical. Similarly, all neutrons are identical. Atoms usually have as many electrons as protons, so the atom has zero net charge. A proton has nearly 2,000 times the mass of an electron, but as positive charge is equal in magnitude to the negative charge of the electron. So protons are a lot bigger than electrons, but their charges are the same. So for attraction and repulsion, here you're showing a couple of pith balls. Here you have two balls that are positively charged. They're being repelled from each other. And then you have a positive and negative that is being attracted to one another. And then you have two negative charges that are being repelled. The fundamental rule of all electrical phenomena is that like charges repel and opposite charges attract. I think this has been mentioned multiple times now, so it might be important. What is the fundamental rule at the base of all electric phenomena? I think it was on the slide right before this. An object that has unequal numbers of electrons and protons is electrically charged. Electrons and protons have electric charge. In a neutral atom, there are as many electrons as protons, so there is no net charge. Whenever you have 5 protons and 5 electrons, they basically cancel each other out, so there's no charge. If an electron is removed from an atom, the atom is no longer neutral. It has one more positive charge than negative charge. A charged atom is called an ion. A positive ion has a net positive charge. It has lost one or more electrons. A negative ion has a net negative charge. It has gained one or more extra electrons. In general, from what we're talking about, mostly it's going to be electrons that move from place to place, not the protons. Okay, electrically charged objects. Matter is made of atoms, and atoms are made of electrons and protons. An object that has equal numbers of electrons and protons has no net electric charge. But if there is an imbalance in the numbers, and the object is then electrically charged, an imbalance comes about by adding or removing electrons. Again, like I said, only electrons are going to be moving around, so only your negative charges move from place to place. You either lose a negative or you gain a negative. The innermost electrons in an atom are bound very tightly to the oppositely charged atomic nucleus. The outermost electrons of many atoms are bound very loosely and can be easily dislodged. How much energy is required to tear an electron away from an atom varies from different substances. When electrons are transferred from fur to the rod becomes negatively charged. Electrons are neither created nor destroyed, but are simply transferred from one material to another. We've talked about something that went like that before. This principle is known as the conservation of charge. In every event, whether large scale or at the atomic and nuclear level, the principles of conservation of charge always apply. Any object that is electrically charged has an excess of deficiency of some whole number of electrons. Electrons cannot be divided into fractions of the electron. This means the charge of the object is a whole number multiplied by the charge of an electron. If you scuff electrons onto your shoe while walking across a rug, you are negatively or positively charged. When you rub rubber or plastic-soled shoes and drag across the rug, they pick up electrons from the rug. In the same way you charge a rubber or plastic rod by rubbing it with a cloth. You have more electrons after you scuff your shoes, so you are negatively charged, and the rug is then positively charged. What causes an object to become electrically charged? Coulomb's law states that for charged particles or objects that are small compared with the distances between them, the force between the charges varies directly as the product of the charges and inversely as the square of the distance between them. That's very confusing, and we'll talk more about it. Recall from Newton's law of gravitation that the gravitational force between two objects is the mass of the first object and the mass of the second object is proportional to the product based on the masses and inversely proportional to the square of the distance between them. This is something we did way back when we talked about gravity and gravitation and stuff like that, these types of problems. Well, Coulomb's law actually kind of works the same way. The electrical force between any two objects obeys a similar inverse square relationship with distance. The relationship among electrical forces, charges, and distance, Coulomb's law was discovered by French physicist Charles Coulomb in the 18th century. So, for charged objects, the forces between the charges varies directly as the proportion as the product of the charge and inversely as the square of the distance. You see how this kind of mocks our other formula that we had worked with before for gravitation? We had the force of gravity, which was m1 and m2 over d squared. Well, here we have q1 and q2 over d squared. And instead of g that we multiplied here, we have k. It's a different constant. So q is our charges. We have charge 1 and charge 2. And d is going to be the distance between those charges. And k is a proportionality constant that we'll get to in just a second. The SI unit of charge is the coulomb, abbreviated with a capital C. A charge is 1 coulomb is the charge of 6.24 times 10 to the 18th. That should be superscripted, electrons. A coulomb represents the amount of charge that passes through a common 100-watt light bulb in about 1 second. The proportionality constant, K, in Coulomb's law is similar to G in Newton's law of gravitation. K is basically 9.0 times 10 to the, let's count it, 1, 2, well, they've already got it right there, 10 to the 9th. 9.0 times 10 to the 9th newtons, meter squared over coulomb squared. If a pair of charges of 1 coulomb each were 1 meter apart, the force of repulsion between the two charges would be 9 billion newtons. That would be more than 10 times the weight of a battleship. All right, Newton's law of gravitation for masses is similar to Coulomb's law for electric charges, whereas the gravitational force of attraction between a pair of 1 kilogram masses is extremely small. The electrical force between a pair of 1 coulomb charges is extremely large. The greatest difference between gravitation and electrical forces is that gravity only attracts, but electrical forces may attract or repel. Very important concept right there. Because most objects have almost exactly equal numbers of electrons and protons, electrical forces usually balance out. Between Earth and the Moon, for example, there is no measurable electrical force. In general, the weak gravitational force, which only attracts, is the predominant force between astronomical bodies. Although electrical forces balance out for astronomical and everyday objects, at the atomic level this is not always true. Often, two or more atoms, when close together, share electrons. Bonding results when the attractive forces between the electrons of one atom and the positive nucleus of another atom is greater than the repulsive forces between the electrons of both atoms. Bonding leads to the formation of molecules. What is the chief significance of the fact that G in Newton's law of gravitation is a small number and K in Newton's law is a large number when both are expressed in SI units? The small value of G indicates that gravity is a weak force. The large value K indicates that electrical force is an enormous in comparison. So electrical forces are stronger than gravitational forces. If an electron at a center distance from a charged particle is attracted with a certain force, how will the force compare at twice the distance? According with the inverse square law, at twice the distance, the force will be 1/4 as much. Remember our inverse square law? If you're 2 times as far away, you then invert it, you get 1/2, and then you square it, 1/4. Is the charged particle in this case positive or negative? Since there is a force of attraction, the charges must be opposite in sign, so the charged particle is positive. So what does Coulomb's law state? That's the end of the notes for part 1.